Okay, so we started last time trigonometric integrals and substitutions. So this is a long section. Let's continue. So I will go to Canvas and bring the notes. Waiting for Canvas, takes some time. Okay, here is our class. And I go to Files. And this is section 6.2. So trigonometric integrals and substitution. So we already discussed a few examples. Here, 1, 2, 3. So next example, we start here. Well, we would like to integrate. You see here you have tangent to even power, secant to even power. Those even powers are 6 and 4, but the technique will work for any even power here and even power here. So U is equal here when you have something like this. So tangent to even power, secant to even power. The substitution U equal tangent will work, as you will see in a moment. So we make substitution U equal tangent x. Then, of course, du is secant square x dx. And the identity we will have to use is something you know from the previous semester or from trigonometry. Secant square x is 1 plus tangent square x. We will be using this identity in many different forms. So kind of to deal with this integral, this is what we will use. Later, we will use this identity in the form that tangent square x is secant square x minus 1. But to deal with this, we will have to know that secant squared is 1 plus tangent. Okay, maybe let's work this example, because here is the answer, but let's work this example maybe on the whiteboard. So I will go stop sharing here, and then I will go and work the details on the whiteboard. So we have to compute tangent 6x secant to the power 4x dx. So again, when you have even power and even power, the recommended substitution is U is equal tangent x. Then, of course, du is secant squared x dx. Let me put this trigonometric identity here as well. So you see, I will put here secant squared x is 1 plus tangent squared x. So that's the identity we'll be using. And you see, we'll be using this identity on many different occasions. So let me put here a bracket. Okay, so integral becomes, let's write it like this. Tangent, and let's split this into two pieces. So secant squared x times secant squared x dx. So now you see that secant squared x dx, this is du. Tangent to the power 6, this is u to the power 6. And this thing, secant square is 1 plus tangent square. So, and tangent is u, so this is 1 plus u squared. So secant square x is 1 plus b. So substituting everything, you will see that we are getting integral. Well, u to the power 6. 1 plus u squared. And this is du. So of course that's a polynomial, easy to integrate. So u to the power 6, so this will be u to the power 7 over 7 plus u to the power 8. So integral will be u to the power 9 over 9. And of course u is equal to tangent. You substitute. So the final answer is tangent to the power 7x plus tangent to the power 9. And we finished. You can add constant of integration. So again, and this trick will work for any even power. Tangent to the even power, secant to the even power, this thing will work. Now, we can also deal with odd power. And that's the next example. So let's go again to share screen. So you see, so this is kind of this example here. Now, you have tangent to the power 5 and secant to the power 7. So odd power, odd power. When we have odd and even, we don't know what to do. Well, it's more complicated, okay? So just to see, that's more complicated. But when you have even odd and odd power, also things will work, but there's a different substitution this time. Well, you should substitute for secant. So u is equal secant theta. You'll see that this thing will work. So let's see if we can see things here. So of course, if u is secant theta, du is secant theta tangent theta d theta. So because of this, let's write this thing in this form. So integral now becomes tangent to the power 4 times tangent. That's tangent to the power 5. You write this secant to the power 6 times secant. That's secant to the power 7. I wrote it in this way because now secant tangent d theta is du. And also here, tangent squared theta, you remember, is secant squared theta minus 1. So we are using this identity we had before, but in different way. Tangent squared theta is secant squared theta minus 1. So using this identity, we have secant squared theta minus 1, that's tangent squared, and then to the power 4, that's tangent 4. Okay, so you see, so this is, we wrote this like this, and now, of course, the integral becomes u squared minus 1 squared. Secant was u, so u to the power 6. And secant tangent d theta was du. And we were able to reduce this trigonometric integral to the integral from polynomial function. That's a polynomial. Of course, to do this, it's not finished. That's u to the power 4 minus 2u squared plus 1. You multiply by this and integrate term by term. So that's how you deal with this. Okay. In general, there are no rules. We don't know what to do. You should try whatever you can. So there's this kind of nice sentence in your book, and I will discuss this. For other cases, the guidelines are not as clear-cut. So to integrate some trigonometric functions, we may need to use identities. You remember I mentioned double integral, double angle formula, power reduction formula, and so on. Sometimes integration by parts may help. Well, and occasionally a little ingenuity. I will illustrate how this thing works. So let's look at some examples. Of course, to integrate tangent is easy. We had this last time. Tangent is sine over the cosine. When you substitute for the cosine, you get rid of sine, and you get this answer. So integral from tangent is natural logarithm secant x absolute value plus constant. And that's easy. Now, let's look at integral from secant. That's a difficult case. And we will deal with this integral in 3 different ways, as you will see here. So I will show you how to integrate this thing in 3 different ways. We will get 3 different formulas. They will look different, but they will be equivalent. So the easiest way, but it's difficult to figure out this trick. It's easy to follow, so you will see that it's easy to follow my explanation, but it would be difficult to invent this. So to integrate secant x dx, let's multiply secant x by 1, and 1 is written in this way: secant x plus tangent x divided by secant x plus tangent x. That's of course 1. So nothing changed. However, when you make this rearrangement, now you will see that if you substitute u equal secant x plus tangent x, du will be secant tangent. Yeah, so of course the derivative of secant is secant tangent. Derivative of tangent is secant square. So du is secant tangent plus secant square. And you see that du is the whole thing here. Here we have secant square plus secant tangent. So everything we have here in numerator is just du. So this integral here, after the substitution, again, I'm getting message that my internet connection is unstable. So making the substitution, this integral becomes du. So the whole thing here is du divided by u. That's u. So that's natural logarithm absolute value of u plus constant of integration. Well, if you substitute what u was, we are getting the formula that this is ln secant x plus tangent x plus constant of integration. So that's the simplest way to integrate secant. And it's useful to remember this formula. You'll see that we'll be encountering this quite often. So it's useful to know that formula for this exists, is here. So that's one way of integrating secant x, probably the simplest way, but of course it's kind of difficult to invent this trick. Easy to follow, but it would be not so easy to invent this trick. Now, second, let's try to integrate this using symbolic manipulation package. I will use Mathematica. You will see just this in a moment on Mathematica. I will switch to Mathematica in a moment. So second thing, you see answer using Mathematica. Okay, Mathematica will not give you this answer. Instead of absolute value, there will be parentheses. Mathematica ignores absolute value, or in other words, Mathematica is assuming that what's here is positive and does not put absolute value. So when you are using Mathematica, be critical. If you would put this answer into the web work without absolute value, you would get an error message. So just Mathematica would give you the answer which is not correct. So Mathematica is making the assumption that what's under the absolute value is positive and it skips absolute value. Okay, so let's see if we can go and use Mathematica. So I will stop here, then I will open Mathematica. So share screen. And I have here Mathematica notebook. Okay, so here you see Mathematica notebook. So let's integrate. So of course the syntax is, we will have the whole section 6.4 about symbolic manipulators. So kind of just to see, I will still be using Mathematica here from time to time. It's a very useful package. So the syntax is integrate. Okay, and you would like to integrate secant x. And then you have to tell Mathematica with respect to what to integrate. So I will integrate with respect to x. Okay, and let's see what's the answer. Well, you see, ln, there's no absolute value, there's a bracket. Cosine x plus 2 plus sine x plus 2 minus ln cosine x plus 2 minus sine x plus 2. Of course, you can put everything under one logarithm. So the answer is logarithm cosine x plus 2 plus sine x over 2 divided by cosine x over 2 minus sine x over 2. This is what I had in my notes. So that's the answer using Mathematica. Okay, let me make this comment. So let's see what you will get. Integrate 1 over x. Okay, we integrate 1 over x with respect to x. So look, Mathematica tells us that's a log of x. There's no absolute value, there's bracket. So this is incorrect. If you would put this thing into the web work would tell you that you have the wrong answer. So again, be critical. When you use Mathematica, be critical. Kind of just maybe check the thing also using maybe some other package and so on, kind of. Yeah, but the message here is be critical when you use Mathematica. And I will see, we will be discussing this, and I will see some other things, interesting things about those packages, kind of. But you have to be careful and critical when you use those packages. Don't trust them blindly. Okay, so let's go back to my notes. So you see you have two answers. First one is integral from secant is ln secant x plus tangent x. And another one using Mathematica is this. It's not clear right away that they are the same. Yeah, they look different. Again, they are equivalent. You can show this if you want. But we first go to the method number 3. So that's answer using Mathematica. Okay, let's try to figure this out in different ways. So this next thing will be quite long and kind of quite complicated, but natural. So kind of if you try to integrate this thing, probably this is the way you would choose. That's kind of, again, quite long, as you will see, quite complicated, but more natural. So that's how it works. Well, let's try to integrate secant x dx. Well, secant is, of course, 1 over the cosine. So that's integral from 1 over the cosine x dx. Let me see if I have to admit somebody. I stop for a second, okay? Stop here. No, everybody is here, okay. Everybody's here, so okay. And then let's multiply things by cosine. So you get integral cosine x divided by cosine square x. Why? Well, because now cosine squared is 1 minus sine squared. And then if you make the substitution u equals sine x, du is cosine x dx, and this integral becomes integral du, this is du, over 1 minus u squared. Well, that's a rational function. That's a polynomial. We have 1 over 1 minus u squared. That's a polynomial divided by polynomial. polynomial divided by polynomial, that's called a rational function. Now we will learn how to integrate rational functions in section 6.3. That's the next thing. Maybe we'll start this next time. So treat this as a kind of introduction to integrating rational functions. Okay, so let me go again, maybe, and now let's solve this on the whiteboard. How to integrate this rational function. So again, systematic approach will be discussed next time. So let me stop share. So let me erase this now. So we would like to integrate rational function 1 over 1 minus u squared. Okay, so the approach is like this. Let's write this in different way. Namely, let's work on this. Let's factor out denominator. Well, that's equal to 1 over 1 minus u times 1 plus u. And then we can write this like this. We can write this as a sum of two functions of this way. A over 1 minus u. This is the result in algebra which tells us that when you have something like this, you can split this into so-called, those are called partial fractions. So kind of just this rational function is a sum of partial fractions, where a and b are some constants. So let's try to compute those constants. Well, in order to compute those constants, well, we can do this on our head, as a matter of fact, and I will tell you how to do this very fast in a moment. But first, maybe let's use a brute force. Let's multiply everything by common denominator. Of course, common denominator is 1 minus u squared. So if you multiply everything by common denominator, you get the following. And let's start from here. A, well, times 1 plus u. 1 minus u will cancel, yeah? Plus b, 1 minus u. And this is equal to 1. So now, if you multiply, you get a plus aeu plus b minus bu is equal to 1. So let's write things like this. Let's collect terms in front of u. You have a and minus b. So a minus b eu. And what's left? Plus a plus b. And that's equal 1. And now we will compare. We have one polynomial is equal to another polynomial. So what we have in front, you could write that this is 1 plus 0 times u, if you want to see things better. So comparing this and this, a minus b is, there's no u here, so it's equal to 0. And a plus b is 1. Of course, it's easy to solve this system. If you add two equations, you get 2a is 1. So, of course, a is 1/2. And, of course, from the first equation, a is equal to b. Yeah, so b is also 1/2. So that's how you can compute those constants. But now, you can get those constants really without any computations, kind of, in just. So let me show you how to do this without faster. So let me write things. Let me rewrite things. I will need some space, kind of. So I will write this thing like this. So we are trying to figure out 1 over 1 minus u, 1 plus u. That's equal to a 1 minus u plus b 1 plus u. I wrote like this because I will need some space to explain things. So now, look, to compute a in your head, I will do something, I will write something, but usually you do this in your head, kind of. Let's multiply things, but 1 minus u, and then put u equal 1. See what happens. So, okay, so the thing is like this. Multiply the whole thing by 1 minus u, and then put u equal 1. What happens? Well, then y minus u cancels. 1 minus u cancels. And here we get 1 minus u. Now, see what happens if we put u equal 1. If you put u equal 1, this will be 0. So what you get that a is equal to what? Well, a is equal to 1, 1 plus u, and u is 1. Well, that's 1, 1 plus 1 is 2. So a is 1/2, you see? So we got it without any computations, just kind of, again, you usually do this thing in your head. By just put something just to explain things. Okay, and so of course, same thing is for this other constant. This time, you multiply by 1 plus u, and then you put u equal minus 1 to make this 0. So see what happens this time. Well, this cancels. You multiply this by 1 plus u, and this cancels. So now, b is equal to, if you put u equal minus 1, that's 0. So this goes away. So what is b? b is equal to 1 over 1 minus 1. That's 1/2. So it's the same thing. You see, so that's a faster way of computing things.
So will A and B always be the same value, or will it change?
No, not always the same. That's a special example. You will see in section 6.3, we will have a lot of other examples, and of course, sometimes anything. A can be 1, B is 2, 7, whatever. No, it's not. That's a kind of, for this specific example, only this happened. But in general, those constants are different, will be different. Okay, so see what we got. So conclusion is, from all those things, that 1 over 1 minus u squared is equal to 1/2 1 minus u plus 1/2 1 plus u. Yeah, a, b. So if you integrate both sides, you get that the integral 1 over 1 minus u squared du is equal to, well, 1/2 integral du 1 minus u plus 1/2 integral du 1 plus u. Now, there's a very useful formula. You had this formula last semester, namely, let me put it. If you have f prime over x over f of x dx, who knows what is this? Can you tell?
Isn't it ln of the absolute value of f of x?
Correct. So you see, so this is ln, absolute value f of x. Well, constant of integration, let's forget about this. Yeah, so this is this. So now look, we can use this formula to integrate those two pieces, because what is the derivative of 1 minus u? It's minus 1. So let me put here minus and minus. Minus, minus is plus, nothing changed. But I put here minus because now this is derivative of 1 minus u is minus 1. And of course here, derivative of 1 plus u is 1. So there's nothing to do here. So u is equal to minus 1/2 ln 1 minus u plus 1/2 ln 1 plus u. Well, you can put things under one logarithm, so maybe let me put it here. So, in other words, this integral is, let me put it here. Well, under one logarithm, so, okay, we can put 1/2 under, so it will be square root, and then under one logarithm, so you have ln square root absolute value 1 plus u. You remember u was sine, so 1 plus sine, 1 minus sine. Again, different looking, yeah? So we see integrating the kind of things, first using this kind of ingenious trick, then using Mathematica, and then using this natural way, we got 3 different answers. Maybe let me put those answers again. So one answer is, so this was secant here. So this, the thing was secant x. So one answer is this one. Another one, secant x dx is ln secant x plus tangent. So this was the answer we got using this ingenious trick, you remember. Secant tangent, okay. And then answer using Mathematica was secant x dx is ln cosine x over 2 minus plus sine x over 2. Let me check if there's, I'm not making mistake. One moment. Yeah, cosine plus sine, cosine minus sine. So we got 3 different looking answers. So we will show in a moment that kind of this and this is equivalent, okay? But I will not show everything, so kind of try to show that this is equivalent to this if you want. It's not complicated, just you just put here secant is 1 over the cosine, the sine over the cosine, rearrange things and so on, kind of. You have to use some trigonometric identities, But again, some computations, it's not completely trivial, but that's all three answers are equivalent. But you see, we got three different looking answers. So let me now comment on some of them. So again, let me share the screen. Answer is ln secant x plus tangent x. Answer using Mathematica is this one. And what we got now using this in the kind of partial fractions is ln 1 plus sine x, 1 minus sine x, absolute value here. So now let me show you that what we got is kind of looks more or less like what we got using Mathematica. Okay, so let's work on this. Let's try to rearrange this. Let's work on square root, absolute value 1 plus sine over 1 minus sine. Well, that's equal to. So using double angle formula, sine x is 2 sine x over 2 cosine x over the 2. And same thing here. So 1 plus 2 sine cosine and 1 minus 2 sine cosine. Now, see that 1 plus 2 sine x over 2 cosine over 2 can be written like sine x over 2 plus cosine x over 2 square. Why? Because if you square, you get sine square plus 2 sine x cosine x, x over 2, plus cosine square. And of course, sine square plus cosine square is 1. So of course, you see that that's the same thing. So 1 plus 2 sine x over 2 cosine x over 2 is cosine x over 2 plus cosine x over 2 square. And similarly here, 1 minus 2 sine times cosine is sine x over 2 minus cosine x over 2 square. Check it. It's sine square minus 2 sine cosine plus cosine square. Again, sine square plus cosine square is 1, and we are getting 1 minus 2. So that's the same thing. Now, you see, well, square and square root cancel, and what you get is that this thing, well, is equal to cosine x over 2 plus sine x over 2, cosine x over 2 minus sine x over 2. So kind of those two formulas are equivalent. So ln of this is ln of this. So you see, so we showed that this formula for integral from secant is equivalent to this answer we got from Mathematica. Well, just we added absolute value, of course, but that's the thing. So again, if you want to show that those other things are equivalent, kind of just you have to use some other trigonometric identities and so on. Okay, so this was first part, integrating some kind of trigonometric functions. Now, there's something that is called trigonometric substitutions. Quite often, we have to integrate functions which contain expressions like square root a squared minus x squared, or a squared plus x squared, or x squared minus a squared, where a is constant and x is independent variable. So when you see something like this, the substitutions which are listed here may help. Again, not always, but kind of quite often it will be useful. They will simplify usually the computations. So when you have expression a squared minus x squared square root, make the substitution for x, that x is this a sine theta. where theta is bounded between minus pi over 2 and pi over 2. You will see why we are imposing these conditions when we discuss examples. And as you will see, we will have to use identity 1 minus sine squared x. Of course, it's cosine squared x. So that's the identity we will have to use to simplify some integration. Okay. When you have a squared plus x squared, well, then the recommended substitution is x equal a tangent, where, again, theta is between minus pi over 2 and pi over 2, excluding those values. Now, the trigonometric identity that you will have to use is something already we discussed. 1 plus tangent square is secant square. That's the identity we'll be using when we are making this substitution. Again, you'll see how it works on specific examples. And the third substitution, when you have x squared minus a squared, well, then the recommended substitution is x equal this constant a times secant theta. And again, here is the restrictions on theta. You will see why. Theta is between 0 and pi over 2, or between pi and 3 pi over 2. There's a reason for this, which we will discuss when we have some examples. And the trigonometric identity is the same here, but written in a different way, namely secant squared theta minus 1 is tangent squared theta. So we will be using the same identity here and here, but written in a different way. Okay, so those are trigonometric substitutions. So now let's see how it works. I have the example here, so maybe let's work it on the whiteboard, okay? Because so you see all the details and so on. So we would like to integrate square root 9 minus x squared over x squared dx. So we have this thing like this. So let's see if this substitution will help to integrate this. Again, integrating those things with square roots is quite complicated. Yeah, so that's usually kind of quite a messy thing. So let's work this example on the whiteboard. I will write it and then you will see how it works. So let me stop here. Okay. I'm just looking for this thing in my notes. One moment. Okay. So 9 minus x squared root dx over x squared dx. Okay, so looking at the table, you remember the recommended substitution this time is x is equal, well, we have 3 squared, so 3 sine theta. So that's what's, once you see something like this, that's what you should substitute, hoping that this will simplify computations. Well, so of course dx is 3 cosine theta d theta. And now let's see what is this on the side. So let's compute very carefully to explain all the points. Let's compute this. So that's equal to 9 minus 9 sine square theta. Well, so that's equal to, well, you factor 9 and then you factor in front of this, so it will be 3 square root 1 minus sine square theta. Of course, 1 minus sine square theta is cosine square theta. So that's equal to 3 cosine square theta. And again, I will use this famous formula. Square root of a squared is equal to what? Who knows? What is square root from a squared?
A.
No. Close.
Minus A?
Positive or negative A?
Absolute value of a. So that's the formula kind of. So again, square root from a squared is not a, not minus a, it's absolute value of a. So this is equal to 3 absolute value of cosine theta. Now remember the restrictions on theta. Let me put here. We assumed that theta was between minus pi over 2 and pi over 2. Well, so how cosine theta looks like? Well, so if you draw, if here's theta, theta, see it? Yeah. So here is pi over 2 minus pi over 2, and cosine theta looks like this. Well, what you see that the cosine theta between pi over 2 and pi over 2 is always positive. So this was the reason for this restriction. So cosine theta is positive. So you can get rid of absolute value. And this is really convenient. It's very difficult to integrate functions defined by absolute value because you have to split integrals into pieces where things are positive, negative, and so on. So this makes life much simpler. So 9 minus x squared, let me put it here. I will erase things and we will continue the integration. So let me put what we got. So square root 9 minus x squared is 3 cosine theta. Now let me erase this. I will just because I want to continue here. I will be telling them. So okay. So what we have is that this integral becomes, well, 9 minus x squared is 3 cosine theta. Dx, well, I erased this, but dx was 3 cosine theta d theta. And x, you remember substitution was 3 sine theta. So this is over 9 sine squared theta. Again, maybe let me remind, this was 3 sine theta. This was a substitution. X is equal to 3 sine theta. Okay. So we have 3 times 3 is 9, and 9 cancels. And so we have cosine squared over sine squared. So that's equal to integral cosine square theta over sine square theta d theta. Well, okay, so we can integrate this kind of easily. Cosine square theta is 1 minus sine square theta. Maybe I should write this kind of or dense. So this is cosine square theta over sine square theta d theta. So that's equal to 1 minus sine square theta over sine square theta. So that's equal to 1 minus sine is cosecant. Yeah, 1 over sine square is cosecant. So cosecant square theta d theta minus integral sine over sine is 1. So d theta. Of course, now you should know that, okay, let me put the formula we will be using, okay? So let me erase maybe this intermediate steps. So you know the tangent x prime is secant square. And you know that cotangent x prime is minus cosecant. So again, those are the formulas from the first semester. So of course, you see here we have, so this means that the integral from cosecant square is minus cotangent square. So we know how to integrate this. Yeah. So using the second formula, so let me erase first, we don't need it. So this integral becomes minus cotangent theta. So that's this. Well, here is not a problem, minus theta. Well, we finished. You can add constant of integration if you want. So this is what we got so far. Well, we are not done. We have now to express everything back in terms of x. Yeah, this is, you see, this is theta and kind of. So of course, this is what you do. Let's write this relation like this. So we have sine theta is, of course, x over 3. The same thing. And in order to go back to x, let's draw the right triangle which corresponds to this relation. I will draw the picture and you will see that this is what it is. So I put here angle theta. That's a right angle. And now sine x, sine theta is x over 3. So if I put here x and if I put here 3, that's what it is. Yeah. So check on the picture. What is sine theta? Sine theta is x over 3. So the right triangle which corresponds to this substitution looks like this. Well, but now we need cotangent theta. Well, so we know how to compute this. Okay, so what is this side? Using Pythagorean theorem, this would be 9, 3 squared minus x squared. And looking at this thing, you see from here that cotangent theta is this over this. So cotangent theta is square root 9 minus x squared over x. And again, what is theta? Well, there's no easy way. Theta is arc sine x over 3. So putting everything together, so let me maybe erase kind of those computations. We know that theta is arc sine, cotangent theta is here. So the final answer is, this is equal to minus square root 9 minus x squared over x minus arc sine x. You can add constant of integration if you want. So this is the final answer for this example. So again, we use the right triangle to figure out what is cosine theta. Okay, let's look at one more example. So that again, just let me. So this is share screen. So you see, so kind of just, so that's still first substitution, and then we worked this example. So here you have those details kind of on the notes. Yeah, if you miss something, kind of you have this thing, and here is this. So minus cotangent minus theta. Here this is this right triangle, and so on. And here is the answer. So all the details are on the slides. One more example. Find an area enclosed by the ellipse x squared over a squared plus y squared over b squared equal 1. Well, okay. So that this ellipse looks like this. Yeah, that's a here, b here. A, b are positive, of course. Yeah. Well, so just to compute this area, we compute this area of the first quadrant and multiply by 4. Of course, this area, this area, this area, this area is the same. So that's what will be our approach. We will compute this area here of the ellipse in first quadrant and multiply the answer by 4. So this is the approach. Well, so to compute this area here, let's get this function. How this function, the formula for this function. Well, let's solve this for y. So of course, y squared over b squared is 1 minus x squared over a squared. So y squared is b squared, 1 minus x squared over a squared. You factor out a squared. This is b squared over a squared minus a squared. And if you take square root, you take plus because that's positive. So y is equal b over a square root a squared minus a squared. So again, we have this thing that substitution will be sine. So the area is 4, yeah, because, and then integral from 0 to a from the function, which is b over a squared minus x squared dx. So here you have kind of probably enough details, kind of, yeah. So again, you make substitution x equal a sine, then dx is a cosine. And if you remember, this was a cosine. So if you make substitution, you get that this thing is here. Now also, when you make substitution, you change the limits. That's definite integral. So certainly, if x is 0, sine theta is 0, so theta is 0. And when x is a, sine theta is equal to 1. Yeah, a is equal a sine theta, so sine theta is equal to 1, which means that theta is pi over 2. So kind of, when you make the substitution, you change the limits from 0 to a to 0 pi over 2. That's the function. You factor all the constants, and you get that what's under the integral is cosine squared. So of course we use this power reduction formula. Cosine squared was 1/2 1 plus cosine 2 theta. So 1/2 and 4 gives you 2. So that it's 2ab. And then if you integrate this thing, you get pi over 2. When you integrate this thing, you get 1 over 2 sine 2 theta. When you substitute, you get 0, 0. And the answer is pi AB. And now, again, you have enough details probably just to understand this completely. So kind of that's another kind of example. So let's discuss the second. It's not finished yet, so maybe let's discuss this on the right. I will not finish this exam, only just once we get something that we can integrate, we will stop. So maybe this is maybe the last example for today. Let me again stop sharing the screen, and I will do this on the whiteboard. I will write this again on the whiteboard in a moment. So this is, but you see that now we have x squared plus a squared. So we will use the second substitution, which was 2 tangent. So let me stop here. And I will go to let's see what it is. I'm looking for the notes. One moment. Yeah, 18, 19, 20. Yeah. So we would like to integrate dx x squared square root x squared plus 4. So again, you look at the table of substitution, and if we had x squared plus a squared, recommended substitution was x is equal a, which is 2, tangent theta. You remember here, let me put here so we will explain this. When theta is between minus pi over 2 and pi over 2. So that's the substitution you are making. So of course, let's put here dx is 2 secant squared theta d theta. Yeah, dx is 2 when x is equal to tangent. Dx is secant square. That's what you know again from the first one. So now again, as before, let's compute this on the side. So what is square root x squared plus 4? Well, that's equal to square root 4 tangent square theta plus 4. Well, so you can factor 4 and then 2. So that's 2 square root tangent square theta plus 1. So that's equal to 2. And you remember that trigonometric formula tangent square theta plus 1 is secant square. So 2 square root secant square theta. So that's equal to absolute value secant theta. Now, secant theta is 1 over cosine. So let me draw here. So theta. So maybe, okay, let's put here minus pi over 2, pi over 2. In blue, I will put cosine theta. And of course, secant is 1 over cosine. So secant looks like this. has asymptotes at pi over 2 and minus pi over 2. But again, secant between minus pi over 2 and pi over 2 is always positive. So we can skip absolute value. So the thing is that this was chosen, so we are able to skip absolute value. Okay, so we have everything. Let's see now. If you substitute, you will see that we'll get something not too bad. So now let's substitute what we are getting. Integral. Well, dx integral. And let's go switch everything to sine and cosines. Secant is 1 over cosine. That's secant, 1 over cosine. And tangent is sine over cosine square theta. That's tangent square d theta. Well, cosine cancels, and we get cosine over sine square. This is what I have. Let me check. Yeah. So, of course, we get this thing. So, certainly, you can deal with this if you make substitution u equals sine theta. You'll be able to annihilate this, and you'll have to integrate function 1 over u square, which is, of course, easy. So kind of so we didn't finish the example, but this is how it works. Okay, so this is all for today. I will have still additional examples to discuss those other cases. Again, examples.